Dr. J, finishing up the section 4.6 on applications. No fooling around this time. Now we're going to do this one for real. So we're going to talk today about annual growth or decay, also known as appreciation that's growth, or decay is depreciation. Both types use the same formula. For annual growth or decay, we say A is equal to P times the quantity 1 plus R to the T. If R is greater than 0, it's growth. And if R is less than 0, it's decay. The two classic examples are home values. Not always, but most of the time in these models we assume that the value of your house is going to go up. However, you probably all know this, when you buy a car, it decays over time, it loses its value over time. So we're going to do two examples using this formula, one for a house, one for a car, among other things. So example 1. A house was purchased in the year 1990 for $105,000. By the year 2015, the value had appreciated or in other words grown to $210,000. Find the annual growth rate. And use it to predict the current value of the house. Okay. So we have our principal. That's going to be $105,000. We have our current value or appreciated value, A. Sorry, it's not current, it's the value in 2015. And then we have T. T is the difference between 2015 and 1990. So that's 25 years for T. So we'll set this up. A equals P, 1 plus R to the T, and we are solving for R. So 210,000 equals 105,000 to the 25th power. Our goal is to solve for R. So we're going to divide both sides by 105,000. Coincidentally, that's actually 2. Just to give us a nice number, the house has doubled in 25 years. That might not always happen. We just got lucky. You might not get so lucky. You might get another value here other than 2. Whatever you get is what you get. So come on over here. We're solving for r. So we're going to take the 25th root of both sides. Now you might not have a 25th root button on your calculator. Let's see, do I have a, right here. You could typically find it near the exponent. It's a second function, so we're going to say, you might have to zoom in on this. We're going to say 25 second function, then we're going to do the 25th root of 2. Let's try that again. So we're doing 2 . Let's try that again. 25th root, second function of 2. That's not right. All right, let's try another method then. If that doesn't work, we can use a fraction exponent. I'm not sure why my 25th root button is not working. So let's try, instead of a 25th root, we'll try a 1 over 25 power. So we'll go 2 to the 1 divided by 25 power. There we go. So we get 1.028113827 is 1 plus r. Then we're going to subtract 1 from both sides to solve for r. So r is 0.0281138, etc., etc. I'd like to have 4 decimal places. So you can just say r is approximately 0.0281, which is equal to 2.81%. So that is our annual growth rate. I'll play around with this later and see how I can get the 25th root button to work. This second function should allow you to type any type of root, like a cube root or a 5th root, or in this case a 25th root. If you get frustrated with that and it doesn't work, then you can always use the exponent button, which I think is much easier. Just remember, if you're doing an exponent, your root becomes a fraction. So that should be the value your final answer is. Should match my value here. Okay. So now that we have the growth rate, assuming that all things remain the same, which is not 100% accurate, but for this particular chapter, we can idealize a little bit and assume that everything remains the same. So to predict the current value, we got 2020. You're going to subtract from the year you purchased the house, which was 1990. So that's going to be 30 years. We're going to plug in 30 years. Remember, we bought the house for $105,000. Plug in your growth rate, 0.281138. The more decimals you use, the more accurate your answer is going to be. to the 30th power. And for this example, let's round to the nearest $1,000. So how much is our house worth? You might notice something here. We already know what 1 plus r is. We found it a while ago. So we're subtracting 1 to find the annual growth rate, but then when we go back to actually use our formula, we have to add the 1 back in. So it might behoove you to just keep your decimal as 1.028113827. Just ignore the 1 when you're answering the question, but then make sure when you actually use it, you keep it as 1.0, or excuse me, 1.02. I almost screwed that up. See? 1.02. Make sure you have your decimal in the right place. And do the exponential part first. So you have this value raised to the 30th power. So that's 2.29739671, and multiply that by your original value of 105,000. That gives us $241,226.65. Rounded to the nearest $1,000. That's $241,000. Assuming that the growth rate remains constant. Okay. So next, we're going to buy a car. Example 2. A car was purchased in 1998 for $29,000. By the year 2010, the value had depreciated to a mere $11,000. Same question. Find the annual rate of depreciation, also known as the decay rate, or the rate of change. Also known as the decay rate. And use it to predict the current value of the car. Same formula. Keep in mind, I might need to grab a new pen. Keep in mind that because it's depreciating, that tells us that our R will be negative. Keep that in mind right from the beginning, because if you make a mistake and you end up with a positive rate, you you should catch that and realize, wait a minute, how's my car getting more and more valuable over time? This is not a classic car that appreciates. You know, you have a typical car you buy at the car dealership, it's going to go down in value. So keep in mind the principal is the P. That's how much we originally purchased the car for. The A is the, sometimes we use the letter S for the sale price. Sometimes this is S for sale price, how much you could sell the car for. I don't particularly care. I like to use A, but you might see the letter S in some other examples. So put everybody in here. Your sale price is $11,000. The purchase price, $29,000. So purchase price is P. Sale price is either A or S, whichever you want to use. And then you're going to solve for R. Now what's our T? T is 12. Just use mental math for that. T is 2010 minus 1998. So T is 12 years. So we have the same basic process. Looks like the numbers are going to be a little bit trickier this time. We're going to get 11/29. So now we're going to take the 12th root of both sides. Let's see, so we have 11 divided by 29. And then we're going to take the 12th root. So again, if you can figure out how to use your second function root button, that's great. I'm being recorded right now, so I'm just going to go straight to the power of 1/12. So it's 11 over 29 to the 1/12th power. Let me double check that. I don't feel like I did that right. 11 divided by 29, and then raised to the 1/12. 0.92239. 3479. Let's try that one more time. 11 divided by 29 raised to the 1/12. Yep, there we go. Check that. Double, triple check that's true. All right. Now, we're going to subtract 1 from that. Now this time, I can't just ignore anything. I actually have to subtract 1 because it's obviously not 1 point something. So in the previous example, if your 1 plus R has a 1 in front of it, well then you can just ignore the 1. But in this case, it's not quite that easy. I'm going to get a negative growth rate. 0.077606. Round that to 4 decimal places. So that is 0.7761. See, look at your, I take that back. We're just going to throw away these and make that a 0. If we do a 1, that would be 5 decimal places, so this is going to be 4 decimal places. I had overshot my mark my first time. In terms of percentages, that is negative 7.76%. So that is your annual rate of depreciation, or your rate of change, also known as the decay rate. The purpose of all this is really to make predictions. You want to know what your car is worth now, so we can predict how much could I sell my car for, or did I switch to S? Doesn't really matter. What's the sale value of my car, or the salvage value? S. The Craigslist price. So it's the original price of the car, $29,000. You always go back to the principal value of the car. 1 plus R. Well, remember, 1 plus R is right here. I already have 1 plus R. All right. You can calculate it again by doing 1 plus R, but you already have it. It's going to be 0.922393479. The current value, so the current value 2020, that would be 22 years. 22 years. That's 2020 minus 1998. Some of you were probably born in 1998, and so you are 22, or you're gonna be 22 this year. All right, so remember this base here is already 1 plus R. You could just go back and calculate that again, but I recommend just hanging on to it. Raise that to the 22nd power. So you have $29,000 car. That is depreciated by 0.1691058. Multiply that by 29,000. And now your car is worth approximately $4,904.05. For this problem, it's a strange instruction. I want you to round to the nearest 50. Round to the nearest $50. So 4,904 would just be $4,900. Rounded to the nearest 50 is a little bit tricky. You use a 25 or greater rule. So had this been 4,925, then I would round it to 4,950. So if this is less than 25 or less, you round down. If it's less than 25, you round down. 25 or greater, round up. If it's 24 or less, you round down. So this is definitely less than 24. So we rounded down to $4,900. If you do have any rounding issues, that's not a major concern of mine. My main concern is that you know how to solve the problem correctly. If you're entering it and you're getting some strange results, please contact me as soon as possible, and I will tell you how to enter it correctly. Okay. Well, we're going to enter into a whole new realm of problem solving now that we've seen the basic formula for annual growth rate. Notice it's the same as the compounded annual interest, compounded annually. So if you memorize the annual interest formula, you can use it for a lot of different applications. Next, I just want to talk a little bit about the different formulas that we're going to use for the remaining examples. So there are three formulas that all essentially do the same thing. So we have the first one. Okay. But we would like to write this as a function. We'd like to write this as a function notation. And so we redress the formula by calling our a function of t. Because it's a function of time. So the amount of whatever it is we're talking about, money, we're going to move away from money for the next few examples and start talking about actual things that are changing over time. People, places, things. The principal is a constant. So we like to use the symbol C for constant. The 1 plus r is the base. So we like to use A for base. And then finally, the exponent is going to remain t. So this is what we call the function notation. You could put the dot if it's not clear that it's being multiplied. I think that it is clear. If I do not write the dot, you know that this means C times A, so I will omit the dot at this point. So this is the same formula. Keep in mind the growth rate is A equals 1 plus R, and the growth rate is R. So when we rewrite our function into this, what we call the cat formula, f of t equals cat, C-A-T, the growth rate is not apparent. You can't see it in the formula. You would have to sort of extract it out of the A by keeping in mind that A is 1 plus R. All right? Just keep that in mind. 1 plus R is your A. So let's do an example. A city has a population of 13,000 people. And it is growing by 3.7% per year. How long until the population reaches 28,000 people? Now keep this in mind, the growth rate is 1 plus R. So here we have our R, be 0.037. So coming over here, A is 1 plus 0.037. That's going to be our base. 1.037. That's very important that you don't use 3.7 as the base. It's 1.037. So we have our model, f of t. Some people call it p of t, so that you know that it represents population. Doesn't really matter. You can call it f, you can call it p. Heck, you could even just call it y, because if we were to draw a graph of this, this would represent the y-axis. The initial population is C. So we've got CAT. So we've got 13,000 times 1.037 to the t power. The question is when, how long, so what's t going to be if p of t, population at time t, is 28,000? So we're going to replace our p of t with 28,000. That's what I meant when you can literally just call this y. This is like your y value, and the t is acting like your x value. All right, so we're going to solve this equation. Now this time we're not solving for r. We already know r. This time we're solving for t, so we're going to need to use logarithms. First we'll divide both sides by 13,000. So we're going to get 28/13 equals 1.037 to the t power. I'm going to have to erase the statement of the problem. Hopefully you all read it carefully. A city has a population of 13,000. It's growing by this rate, r. That's our r here. And our question is, when is it going to reach 28,000? So we've got all that written down here, so we can erase this. So now we're going to take the log of both sides. You can use the common log, or you can use the natural log. Really doesn't matter. I think last time I did a problem similar to this, I used the natural. This time I'm using the common. You could be really fancy and use log base 1.037, but last time I checked, my calculator only does naturals and commons. So that's what I'm going to use. Bring the t down to the front, becomes the coefficient. Keep in mind that your only variable now is t, so these logarithms are constants. I'm going to divide both sides by the log, 1.037, and I'm going to enter this into my calculator very carefully. So I'm going to do these separately. If you have a more sophisticated calculator, you can do it all in one stroke. So first I'm calculating 28 divided by 13. That gives me 2.15 approximately. Then I'm going to take the log of that, and so that's my numerator. Now you can save that in your screen, but I'm actually going to clear it out and do the denominator now, 1.037, and then do the log of that as well. 5778756. And then now I'm going to divide these results. Now remember, I'm using a very simple calculator. It's just what I'm used to. I also like to feel each and every step. That way if I make a mistake, I just made a mistake, I could feel the mistake. When you put everything into a machine and then you press the button, you can't feel what's going on. If something goes wrong, it becomes very difficult to root out the problem. And so I get approximately 63.3763 years. I will accept the nearest year. I don't need decimals. So round to the nearest year. So look at the 10th place. 5 or greater, nope. So throw that away. So it's going to be 63 years. So that means if a city, in this particular growth rate, if the city had 13,000 people, 63 years later, it would have 28,000 people. Example 4. A bacteria, or a sample of a bacteria, so suppose we're in our laboratory, contains 8 cells. So, you have some petri dish or something in science class, and you've got 8 little bacteria cells. Eight cells in our sample dish. That's supposed to be a petri dish. You can tell I haven't taken chemistry in a long time. After 30 minutes, the sample had grown to 24 cells. So 30 minutes later, in my dish, I've got 24 cells. I think that's 24. How many cells will be present after 5 hours? So what do we got? We got well, f of t, or you could just call it y if you like. You can also call it p of t for population. CAT. Now we have a little bit of a discrepancy here. We're talking about hours and we're talking about minutes. All right, so I think it's better to represent t in terms of hours, but you decide how you want to represent t. Once you've made your decision, you can't change your mind halfway through the problem. So I'm deciding at the beginning that I want to represent t as hours. All right, so therefore 30 minutes, t becomes a half an hour, 0.5. You do have another option. You could keep your 30 minutes as 30 minutes and say, okay, let t represent minutes. If you make that choice, you make your bed, you have to lie in it. That's not a bad bed to lie in, but what would happen is your time would then be minutes, and then 5 hours would have to be, what's that, 300 minutes or something. I don't know what 5 hours is. Yeah, 5 hours is 300 minutes. If you want to do that, then you just have larger numbers. You'd be using numbers like 30 for 30 minutes, and 300 would be 5 hours. I'm going the other way. 30 minutes is a half an hour, and then 5 hours is just 5 hours. All right, so the original population is our C. So this is our C, original population. 24 is our F of T. 24. So after 30 minutes, the time is going to be a half an hour. We have 24 cells after 30 minutes. Our goal is to solve for A. We were given the time this time. So we're going to divide both sides by 8. We get 3 equals a to the 0.5, or if you prefer, a to the 1/2, or if you prefer, the square root of a. Yeah, that's nice. The square root of a. Now you know why I chose to represent it that way. Otherwise, this would be the 30th power, and it would be a lot. It would be the same result. It would just look worse. All right. I think it's clear now when you write it as a square root what you need to do. You need to square both sides, and you're going to get your base is 9. Although I'm not asking it in this question, I just want to do a little FYI for your information. If A is equal to 1 plus R, that means your growth rate is 8. That's 800% hourly growth rate. It's not part of this question. It's just a little side note. If you wanted to advertise or you wanted to tell people, oh, this bacteria is growing so fast. Well, how fast is it growing, doctor? Well, the bacteria seems to have an hourly growth rate. It's not annual, but it's hourly because we're measuring our time in hours of 800%. That's what 8 represents as a growth rate. So keep in mind that when you find your A, that's always 1 plus the growth rate. In this case, the growth rate is 8. We still haven't answered our question. Our main question is how many bacteria will be present after 5 hours. So we have our model. Our model is population of T, or you could also call it F of T, same thing. That would be 8 times 9 to the T power. Now we can use this model to predict how many cells will be after 5 hours. So I've got P of 5, the population after 5 hours. Be careful with the 8 and the 9. Keep them separated. The 9 goes first, and then you multiply by 8. You're going to get a very large number here. Let's see. 9 to the 5th power times 8. 472,392 cells. That's how many after 5 hours. So Might as well do it. After 5 hours, well, it's actually 4 hours and 30 minutes. Because we've already gone 30 minutes and now we're doing an additional 4 hours. So the total is 5 hours. This is what our Petri dish would look like. I know, this is just silly now, but what the heck. You come back 5 hours later and the whole tray is just full of bacteria everywhere. I'm not sure how many of you take chemistry, but maybe you do experiments like this in class. I don't know. They let you play around with live cultures. Maybe, I don't know. Maybe I should talk to one of my colleagues about that.